Yeah, the sticker. Can I remember how to do the stickers is the real question. Smileys. 100% excellence. Okay. Oh, no. That's not what I wanted. And that's really not what I wanted. Okay. The stickers cursed the TV and broke it. You can't see my screen right now, but that's okay because we're going to talk about the word standard of excellence. On the top of the page, you see standard of excellence? Yeah. You guys should hear that in all of your diploma classes. Your tests will be broken into different types of questions. So there'll be like acceptable standard and then standard of excellence standard. You've probably been getting these types of things like since grade 10. It's just that they didn't talk about it explicitly. So when you write a test, 80% of the test will be acceptable standard. That means it's like kind of like a fair, you should be able to do this. It's just a basic outcome. And then about 20% of the test, so 1 out of 5 questions, will be a standard of excellence question. Typically, there's like a bit of a twist to it, right? It's usually something you haven't seen before. In math, it's also usually like 2 concepts blended together, meaning that you're going to have to do 2 things at once. At this point, we've really only learned logs. So this is standard of excellence, but it's not the type that we'll see later in the year where we'll see like 2 units combined into 1 question. That's our usual standard of excellence stuff. It's honestly not going to be that bad if you rely on like what strategies do you know, right? So if I look at this, the question just imagine just says solve. That's all it's going to say, solve for x. Okay, look to see where x is. X is up here. It's in a log and it's in the exponent. So it's in both right now, which is why this is a standard of excellence question. So our strategy. Our strategies are either turn logs into exponents or turn exponents into logs, one or the other. This log is in an exponent. Like there's no way I could turn this into like another exponential form. That would not go smoothly for me. But what I could do is I could change this form so that the exponent was no longer the exponent. Right? I could get that log out of the exponent by changing this into log form. So that's what we're going to do to start this question. When we write things as logs, you go log. The base of the power becomes the base of the log. That's the base of the power, right? 3. So that becomes the base of the log down here. Inside the brackets is whatever was on the other side. So 8. And then the exponent goes to the other side. In this case, the exponent is a log. So it looks like this. So I've taken that power and I've turned it into log form to get rid of that exponent. We feel okay with that? I try to color code it somewhat so you can see where things moved. Right? Base of the power, base of my first log. Other side comes into the log, equals exponent. It just happens to be that exponent's also a log. Okay, from there's a couple of different ways to tackle this question. The way I would look at this question is they're both base 3. Like I would notice, hey, this is log 3. This is log 3. That means if I could make these arguments equal each other, then both logs would equal each other. Fair to say? So if I could, yeah, it's just 2. So if I could make 8 equal 4x, then both logs would equal each other. You're going to divide 4 to the other side. That means 2 equals x. the math behind that's not crazy, right? Like, I didn't do anything that's earth-shattering. I switched to logs, and then we did like a little bit of algebra. It's the intimidation factor that's super high on that question. Like, you look at that thing on a test, and you're gonna be like cussing my name probably. And be like, I don't like, you never showed us that, right? Like, that's the feelings you get. You have all the skills to do it. It's just intimidating. It's just scary. All right? Yeah. Okay, let's try another one. The one beside it also looks very intimidating. Because there's a log inside of a log. And then it's like, now what the heck am I going to do with that, right? Same thing. I'm solving for x. I'm going to rely on strategies I know. So if I have logs, I could turn them into exponents. That's the only real skill I know when it comes to logs. So let's try it. This is going to be my main log. So that's the one I'm changing into an exponent right now. If you could see what I'm circling, that'd be nice. There you go. That's the one I'm going to try to turn into a power. If there's no base on a log, what's the base? Perfect. So this is an invisible base 10. That means my power will be base 10. To the power of 1 equals our argument in here, which happens to be another log. Now, typically in these like intimidating looking questions, once you start on a path, things should either go really good for you. It's like, oh, that's actually not so bad. Or it's going to get really messy because you made a mistake, right? This actually turns out really nice for us. It's like, what's 10 to the power of 1? It's just 10. So I really have 10 equals log 2 of x plus 1. And I've turned this essentially into like a basic log question. X is now part of this log. So let's turn it into an exponent again, right? So let's go back into power form one more time. Base of the log is base of the power. Whatever was on the other side becomes the exponent equals the argument, x plus 1. My logs are now all gone. I can move my 1 over. It would look like this. 2 to the power of 10 minus 1 equals x. Make sure that you just like follow BEDMAS here a little bit. Like, that's why I want to show you like this. It would not be 1 to the power of 10. Right? Sometimes people do silly things. You do all this hard, complex math, and then you forget BEDMAS. You have to calculate the exponent first. So calculate what 2 to the power of 10 is, and then subtract 1. If you're on your calculator and you're not sure where the exponent button is, I need to switch my view here so you can see it as well. Oh, where's my TV? There it is. This is your exponent button, right? So we'll go 2, exponent, 10. If you have a newer calculator, it actually puts into the exponent, which is nice. If you have an older calculator, you actually just see the arrow pointing. Same thing. That equals 1,024, and then subtract 1. That means the answer is 1,023. Uh-oh. 1,023. It's a good thing I didn't have any other crazy tabs open there, hey? Like, just days in Sweden Math 30-2. That's good. That could have been worse. All right, looking at both those questions, So like if that's on a test, that's one of the hardest questions you get on a test. That's standard of excellence. That means that's like the 1 in 5. That's not that bad. It's the intimidation of everything that makes it terrible. And as we get closer to test strategies, like we're going to talk about them. And it's things that you should take into your future life in university, right? Because you're going to be in some intimidating classrooms come college and university. And you're going to have some intimidating tests that you have to write. So it's good to have strategies. Strategy we use is like find what you do know about powers and just start applying it and see how it works out. Don't let the craziness of the question overwhelm you. Yeah. Was it that bad, Kylie? Yeah, it wasn't that bad, right? See? It's not that bad. Okay. Diploma style questions. My guess, I didn't put these on here. Michelle would have. My guess is that these came from a diploma exam. Okay, so she probably found these off of an old diploma. Let's try them together. So, if log of x, y equals a, then an equivalent expression for y squared is. Again, they never even talk about y squared. Agreed? They just give you this. What do I know I can do with logs? It's like the only thing we know how to do with logs right now.
Change that.
Yeah, change into a power. So let's do that. Let's change that into a power. And then let's see if we can't do something with y squared, whatever that is. So to change this into a power, you take the base of the log, x, that becomes the base of the power. Whatever was by itself becomes your exponent, equals your argument, y. What I just figured out is that y equals x to the power of a. Agreed? Perfect. Now let's try to answer the question. What does y squared equal? Well, y squared means you squared both sides. So y squared equals x to the power of a squared. What's our rule when we have an exponent with an exponent? We multiply it in. All right, so that 2 is going to come in. That will be y equals x to the power of 2a. The answer is C. Beauty. When it comes to multiple choice questions, one of the biggest mistakes people make is they look at the answers first. Like in some subjects, that's an okay strategy. Like reading comp, that's not a bad strategy. Like maybe you read the question and the answers and then go to the text. Sure, okay. In math, it's very rare that I would look at the answers before trying to do the question myself. The way I approach a math test, this is my answer key. I'm going to try the question, and then I'm going to see if my answer is in the answer key somewhere. Right? Like that's honestly how I approach it. If it's not there, then I go back and I retry the whole question all over again. If they can predict my mistake, good on them. If they predicted my mistake and the answer is there, that's awesome. Good for them. Whatever. That's the way it goes. But I don't look at the answers and try to make them fit the question. That's like a sucker's move. Right? So always try to answer the question first, then check. All right. Here's another one. We have if 2 over 3 log n x equals 5, then x squared is equal to. Perfect. Okay. You have 2 over 3 log n x. I should have left what I had up here with the grade 10s on the board because it's actually going to be relevant to us. What does this mean if you have like 2 over 3 log n x? There's something happening here that they don't write. It's right in between. Yeah, it's multiplication. All right, so if there's nothing in between numbers and letters or numbers and logs, It means multiplication. Good. So this is 2 over 3 times log n of x equals 5. They ask me what x squared is equal to. I have no idea. But I look at my question. I realize it's a log question. And I'm going to apply the only strategy I know, which is turn it into a power. Currently, I can't turn that into a power. The reason I can't turn this into a power is because of that coefficient, that 2 over 3. Right? The only way you can change things is if log is by itself. Log's not by itself right now. That's 2 over 3 times the log. So I need to get the log by itself. I'm just going to move over here so I have room to work. It's 2 over 3 log, was it n of x? Yeah, thank you. Equals 5. Okay. To turn that into a power, I have to get the log by itself. So I divide 2 over 3 to the other side. You could multiply by 3, divide by 2. That works too. But I'm just going to divide 2 over 3 to the other side. To put that in my calculator, it looks like this. 5 divided by bracket 2 divided by 3. That means 5 divided by 2 divided by 3. Notice that I put brackets around the fraction. It's because I'm telling my calculator, like, that's what I want to divide by, the whole thing. You hit enter. It's 7.5. I'm going to change that to a fraction. It's 15 over 2. Therefore, I now have log n of x equals 15 over 2. Right? I put brackets around this in my calculator. Okay, now what can I do? Change it to exponential form. Perfect. Base of the log, base of the power. So that means n goes to the bottom. Whatever was by itself goes to the exponent. So that is 15 over 2 goes to the exponent equals the argument x. Just like the last question, I now know what x equals. X equals n to the power of 15 over 2. They asked for x squared. So same trick as last question. You're going to square both sides. That means x squared equals n 15 over 2 to the power 2. You bring that 2 in. 15 over 2 times 2 is just 15. My answer should be n to the power of 15. Now I go look at the answers. Make sure it's there. It is perfect. The answer is A. Hello, President. Yes, sir.
So that's my question. So 15 over 2 is equivalent to 7.5, right?
Yep.
And so when you're multiplying the power of power law, and you multiply the two together, for me it looks easier if it's just 7.5 times 2. So is it okay to leave it as a decimal, or should you change it to a fraction?
Yeah, it's good to leave it as decimal. So if you want to leave it as 7.5, that's fine. Mainly because it's a terminating decimal, right? It's 7.5 and it stops. If it was something crazy like that kept going on, and that's my only fear is that people round it, that's when you get into a little bit of trouble. But as long as you're using the entire decimal, you should be fine. All through high school, I was the master of hating fractions and doing everything as decimals. So I fully get that. Why am I not doing decimals? Decimals are easier. I get it. Then I went to university and learned that they never, ever, ever do decimals. And it became fractions all the time. So now, like that I'm here in this position, I try to show you fractions more often than not, just so you're kind of used to it. It was a shell shock to me. I remember my first year being like, why are there fractions everywhere? It's because they use fractions for everything. And I hated it.
Why do they like press decimals so much in high school?
I think the elementary does because decimals are easier to comprehend. 7.5, you can place that on a number line, right? When you're little, like you know what 7.5 is. 15 over 2 is a lot harder to comprehend. Like where would that be on a number line for like little kids, right? So then once you get good at decimals at a young age, then the teachers just keep going on the decimal train because you're good at it. So nobody wants to get off the train that you're good on. That's my guess. You guys also get like the crutch of like your calculator can do fractions for you, which helps a lot. All right. Let's do some graphs. Yeah. Yeah. Okay, we're going to graph exponential functions, which we already know how to graph. We know that exponential functions should look something like this. Right? Like that's what our exponential functions look like usually. Okay, we're also going to graph a log function. And we're going to see how they relate to each other. And they must relate in some way because like powers and logs go back and forth in between each other, right? So they're going to relate somehow. Let's start by doing our exponential function. Okay, we're going to graph all these points given all these y values. So if we put x equals -1 into our calculator, we would get y equals 0.5. So that gives us our first point on our little graph over here, -1, 0.5. Do I just shut that door for me, please? They're going to be loud as they walk through the halls. Yeah, thank you, buddy. If you do your next point, you put 0 in for x, y to the power 2, y equals 2 to the power 0, would just be 1. So I have a point right here. Try the next one. 2 to the power of 1 over 2 is 1.4. So it's somewhere in here. Oh, this is getting tight. Hold up. I need to zoom in a little bit. Maybe I should have done a different scale, but hey. Once you've already made a mistake, you should never fix that, right? Just keep making the same mistake. My next y values that I'm going to plot would be y equals 2. Then it'd be y equals 4. And we start to get that exponential curve. Then it'd be y equals 8. And then y equals 16. And y equals 32. I don't think we're going to be able to fit that one on there, maybe. No, 32 is going to be too far gone. 8, 16, 9, 10, 11, 12, 13, 14, 15, 16. And 32 is off my chart, right? It's way up there. Oh, I just assumed it was 2 to the power 5. I assumed it went in order. What was it? What? Thank you. I just kept going in order. Either way, you should have those points, which means your curve looks something like this. With arrows on the end. Notice that I don't cross that x-axis, right? We learned about that earlier. That's our asymptote. We're not crossing that axis. And it came out kind of exactly like we thought it would.
decimal.
Yeah. Like, try your best if you can. But yeah, it's pretty hard to get some of those decimal ones, right? That's not new. That should look familiar from the first day. Now let's try a log graph. Okay, we know there's going to be some sort of relation here because powers and logs are so closely related. So let's just try calculating some. We're also going to practice calculating logs because we haven't done that in 4 or 5 days, whatever it's been. So let's try log 2 of -1. To put that in your calculator, you have two options. Option number 1 would be to do log base. So you go math log base 2 -1. Then you get an answer of not possible. Perfect. If you try the other way, which would be log -1 divided by log 2, remember that's the other way to put things in your calculator, you should get the same result. Not possible. Okay, the reason why that's not possible, if we think about what we're doing here. Oh, I need space to write. We think about this. Y equals log 2 of -1. Agreed? Okay, if you change that into exponential form, that would be 2 to the power of something equals -1. There is no way that you could put a power, an exponent on 2, and turn it negative. It's not possible. Exponents mean you're multiplying by yourself. All right, so I'm never going to do 2 times itself to turn into a negative number. Never going to happen. That's why you get error. That point does not exist. Just going to put an X in that box. Yes, sir.
You also get an error because there's a vertical asymptote at x to 0.
Yeah, we just haven't built that yet. Yeah, but we will have a vertical asymptote here. And you get that because you're going to notice that you can't do any negative arguments. Like, it's just not possible to get a negative with a positive power. Just not possible.
Could we just put this into the table function?
100% you could. Next one, calculating log 2 of 0. Again, you could type it in with log base, or you could type it in using change of base like that. So log 0 divided by log 2. You also get the same error because of the exact same problem. You will never be able to do 2 to the power of something equals 0. It's just not going to happen. Come back here. That point, not possible. Now we get into some possible points. We have 1 over 2. So log of 0.5 divided by log of 2 is -1. That means we have a point right here. Do the next one, log 2 of 2. And it equals +1. Sorry. I did one too soon. I can hear you muttering. I was like, what are they talking about? I missed log of 1. I was like, and that's not in the right spot, so I know that's wrong. Log 1 over 2 would be 0. That means that goes right here. The next one I already calculated for you. It was 2. No, it was 1. Jeez Louise. Right here. Log 2 of 2. Log 2 of 2 should be 1.
Isn't it 2?
Right here.
I'm confused.
If x equals 2 into this equation, that'd be log 2 of 2.
Yeah.
I think you put this value in. You looked at the wrong column. Yeah. We're doing these inputs right on the left side. And you put in the blue answers in. Yeah. If you did 3, so log 3 divided by log 2 gives you 1.58, like this. Log 4 divided by log 2 gives you 2. Which is right here. And our last one, we actually will be able to put this on there, I believe. So log 8 divided by log 2 is 3. So 1, 2, 3, 4, 5, 6, 7, 8, 3. You get that. You can see a bit of our trend that we're creating here. That's not what's on my computer. Which is probably a bigger problem. Give me a second. Computer is dying. There we go. You should see a trend. Yeah? It's kind of like an exponential form. It's got that same kind of curve feel to it. Except instead of going like up really quickly with blue, it's like turning right really quickly. So it should look kind of like this if you were to ever graph it. It goes right along that y-axis now. And it curves up like this. That is what our basic log graphs will look like.
So they're always in the quadrant?
Not always. We're going to have like ways that they do actually flip around on you. But when we have a base that's positive like this, that's typically the pattern that it's going to make. Miss Schaub had a cool story about it. Remember this? Okay. I'm going to butcher Miss Schaub's story on what a log graph looks like. But you have a tree. Yeah? Tree. Here's my tree. It's got a sweet top. Look at this. What a beautiful tree. Yeah? And it's got all these roots in the ground. Whoa.
Like square roots.
Oh my God, I feel like this story could get so much better, Cecily. This is good. Okay. How do logs get made? They get made when trees fall over. The roots stay in the ground, but the log falls over. That's my log. I don't know what that is. Yeah. But her idea was like a tree falls over, right? And the roots still go straight down into the ground, but then the logs fall over. That's why you get this graph. Roots are straight down, log fell over. I think it's actually a pretty good little story. I just botched it for her. So, if you want a good story, go talk to Miss Schaub. She'll do her log story. She loves stories and songs to help her out.
You saw what you were talking about the other day. She sung it for us
In calc? It's something about the bottom and the base or something, right? Things to notice. With log graphs, we have an asymptote. Just like we had an asymptote for exponential form. Our asymptote's somewhere new, though. Our asymptote is now the y-axis. Right here. There's a line there that log graphs can't cross. I kind of showed you why that happens, right? Because you can't possibly use exponents to turn into negative values. You also can't use exponents to turn something into 0. It's not going to happen, which is why that's the border of where you can't cross. Fantastic. Let's move forward. Domain, range, x-intercepts, y-intercepts, and asymptotes. Let's compare these two things. So, my domain for exponential functions was XER. right? You could go forever to the left, forever to the right on those exponential functions. Your range for an exponential function was y is greater than 0. Remember, on our exponential functions, it was up. It was in quadrants 1 and 2. Never did it go below 0. Never did it equal 0. So there's no equal sign there. X-intercept. There was no x-intercept. Not one there because you can't cross the x-axis. Y-intercept. The y-intercept of all of our exponential functions that we've looked at so far have all occurred at 0, 1. And our asymptote for these functions have all been the same. They've all been the x-axis, which is written as y equals 0. That is your horizontal asymptote. Now let's do log functions and see how things change. If we look at a log function, and I said, what's the domain of this log function? Domain is how far left, how far right. This graph will go forever to the right. However, it can't go forever to the left. It's got a border it can't cross. That border is at 0. That means that x is always bigger than 0. Your domain is x is greater than 0. Notice that it's not equal to 0, right? It's just greater than. For log functions, your range, that's how high a graph goes and how low a graph goes. It goes down forever. That's pretty clear to us. It actually goes up forever too. It is on a bit of an angle. So if you kept zooming out and looking at more of this graph, it is going up. Just very, very slowly. But it is going up, meaning that this range is YER. The x-intercept. If you tried an x-intercept on our log, we did one on this one. The x-intercept was at 1. If you tried the x-intercept on this one, x-intercepts are when y equals 0. And you tried to figure what value would go in there. That would be 10 to the power of 0 equals x. And you would get the same x-intercept of 1. All your x-intercepts at this point will be at 1, 0. Your y-intercept of a log graph does not exist. There's no y-intercepts. The reason there's no y-intercepts is because there's an asymptote there. That asymptote is at the y-axis. We call that a vertical asymptote. The equation of that axis is x equals 0. Awesome. Look at those two charts. And you should notice that something's happened. All the x values and all the y values have just switched. But if you look at your domain for exponential, it became your range for your log. Look at your range of your exponential. It became your domain of your log. Because x's and y's have switched. Look at your x-intercept. It's now your y-intercept. Look at your y-intercept. It's now your x-intercept. X's and y's have changed roles. Look at your equation of the asymptote. It was the axis, x-axis. Now it's the y-axis. It was y equals 0. Now it's x equals 0. It's flipped. Okay? And the reason it's flipped is because these are two, they're like inverses of each other, essentially, right? They're opposites of each other. Log and exponential form. They go back and forth into each other. if you look here, that is what your calculator should show you if you were to graph those two equations, 2 to the power x and log 2 of x. There and there. This line that's going through the middle, that big red line, that line is where y equals x. You should notice that these are mirrored images of each other. Essentially, if you folded your paper on that line, this graph would now be that graph. They would go right on top of each other. They're reflections of each other. Term you haven't seen in a long time, right? But they are reflections about the line y equals x on a diagonal. This also means that if you took any point, let's see if this works. Take a point on one of your graphs. Let's say this point right here. Ooh, can you see green on there? A little bit? What's a better color? Purple? If you took a point on one of your graphs, that point is at 1, 2 on the exponential function. You could find that point on the log function by switching x and y. So this would convert to be 2, 1. And if you look, there's the same point. Because they're reflections, right? That works for any point that you want. Yeah.
Could the two graphs like intersect at any point?
Pardon?
Could the two graphs, if it's a different number, they intersect?
Like land on that line?
Yeah.
On that red line? No, because it's like you fold it over. So the only way that would happen is if this line was already touching this line. Then that would happen. But if you took any point on here, it'll flip to the other side of this line. Right? It's like it's folded over to it. It's kind of a weird thing to picture, right? Yeah. Take another point. Take this guy right here. That is on the exponential graph. That point is 2, 4 on the exponential graph. If I wanted to find it on the log graph, the x and the y would switch spots. And it would be at 4, 2. If you look at the log graph, there's 4, 2. Yeah. So exponential and logs are like full opposites of each other, flipped of each other. It works for any point. It also works the other direction. So if you had a point on your log graph, say this point way out here on the log graph is at 8, 3. You could find that on the exponential graph by switching those spots. 3, 8, it's way up here. Right? They match up. Yes, sir.
You've got them backwards. You put the log 1 into the 6.
Yeah, sorry. I'm trying to show you can go from log to exponent. It is crazy. Does that fix that?
Does the middle line have a name?
The y equals x line?
Yeah.
I don't think so. You just call it y equals x.
Is there a reason why it's y equals
Yeah,
x
what-
on x?
Yeah, because every point on that line is where y and x are the exact same values. So like 1, 1, 2, 2, 3, 3. It's where y and x are the exact same values.
Is there ever x equal
X equals y would be the same thing, yeah.
Okay, so it doesn't matter.
No, I mean, you would call it y equals x, but technically x equals y would be fine too. Yeah, call whatever you want, as long as you have x equals y and you know it's a diagonal line like that. Okay, these things are inverse of each other. They flip back and forth. Yes, sir. The red line?
Yeah, we pick a red line. I can do that.
Yeah, it'll always fold over that y equals x. That line's not going to change. Cool. That's log graphs and exponential graphs. The word I keep using is inverse. Okay, it's because they're opposites. That's what inverse is talking about. It's like the opposite of something. It means that y and x have switched spots for each other. If you think about what that looks like, when we look at our exponents like this, and we switch them into logs like that, you can see how the inverse actually happens. The c became the base, the x is now over there, and the y is now up in the top spot. You'll also notice that this is x isolated. Right? X is by itself. And this is y isolated.
Why is that?
Because when you do the inverse, it should go the opposite. It's getting the other one by itself. Right? You're switching it. Awesome. Ways to write exponential for inverse functions. You're going to see, I think this way, that. Actually, I want to write it the other way first. You're used to seeing this. I want to write what you're used to seeing. You're used to seeing this.
You might need to like restart.
Yeah, it's very blurry. Is it there?
I hope it's blurry on the video.
You're used to seeing that like talked about. Remember function notation? Grade 10. You would have saw f of x equals, and then it gives you a big equation. And so your teachers would have been like, f of x equals y. It's the same thing. It's the same terminology.
I did not understand that at all.
Yeah, what it means is like something is a function of x. So as you choose an x value, you get a result, which is why it changed from y equals to f of x equals. Typically, you saw it in word problems. Right? You would see like, oh, someone kicks a ball and it creates a function as a function of time or something, and you get f of t or f of x. Okay, to do an inverse, you would reverse that. So now you're going to do f of y. And now you're switching it so that you're going to have y is what you're choosing to give you a resulting x value. That means inverse. When you see that, that's what they're talking about. They're saying take the xy values, take the y values, switch some spots. The other way that I've seen inverse written, again, you're used to seeing this, f of x. That's our typical way of writing things. And now you're going to see with a little -1 exponent. So it looks like this. Again, when you see that, it's whoa. Oh, now she's really gone.